Hello, am I audible to you? Okay, then we shall start. So, today I am going to discuss about the Rankine cycle. Uh, Already we have studied it, but let us revisit those things in a quick manner because we are expected to learn some additional things in the Rankine cycle. The additional things which are expected from you at final year level are the reheating and regeneration cycle. That is basically the modifications in the Rankine cycle. So, is it visible to you? Okay, so let us see this. We'll first look at the working of the Carnot cycle. In the Carnot cycle, you are familiar with this. This particular diagram I am interested in basically. The process 4 to 1 is the process of heat addition into the boiler. Process 1 to 2 is the isentropic expansion of the steam. Process 2 to 3 is the conversion of that expanded steam into mixture of water vapor and steam, and then at point 3 anyhow we have to terminate this process, and then the things are compressed back to the boiler pressure through this another isentropic process 3 to 4. Means overall in a Carnot cycle there are 4 processes, out of them 2, that is process 4 to 1 and process 2 to 3 are the constant pressure and constant temperature processes, whereas 1 to 2 and 3 to 4 are the adiabatic processes, reversible adiabatic processes wherein the entropy remains constant. Now, if you see the interactions, during process 4 to 1 we have to supply the energy at higher temperature T1, then process 1 to 2 we are getting the work output W turbine, then process 2 to 3 the heat is being rejected at lower temperature T2, and process 3 to 4 is the isentropic compression, and that's why we need to give the work to the system, that is to the working fluid. Means the net work obtained from the cycle is the work done by the turbine, work obtained from the turbine minus the work required for this compression process 3 to 4. So if you analyze this process, we are getting a very simple equation, that efficiency of the Carnot cycle, which is nothing but the ratio of the work done, that is, as I already told you, the subtraction of the turbine, subtraction of the pump work from the turbine work, that is work done, and the heat supplied, that is the heat which is supplied during process 4 to 1. So if you take the ratio of these two things and if you write down them in terms of the entropy changes, simply we are getting an equation which is in terms of the temperatures. So this is a special thing about the Carnot cycle, that the efficiency of the Carnot cycle for any, maybe a Carnot refrigeration cycle, Carnot vapor cycle, Carnot gas cycle, any Carnot cycle, irrespective of the working fluid and irrespective of for what purpose that cycle is being used, we are getting the performance of the cycle only in terms of the temperatures. And here you can see this equation. The equation is very simple, that it is just a minute, I am just adjusting it slightly. Okay, this equation now this is, I think it is readable to you. This equation shows us that the Carnot cycle efficiency depends on two important factors, that is the value of T1 and value of T2. If you want to improve the efficiency, the temperature T1 shall be as high as possible and temperature T2 shall be as small as possible. So if you want to achieve highest efficiency, you have to supply the energy, supply the heat at highest possible temperature and reject the heat at lowest possible temperature. It means, in other words, when we are adding the heat, where we are adding the heat? We are adding the heat into the boiler, that is during the process 4 to 1. Okay, this heat addition process shall be taking place at highest temperature and the heat rejection shall be taking place at lowest temperature. These two principles are giving us the idea about the efficiency of the Carnot cycle. Now, what are the limitations of the Carnot cycle? Although we know that through our experience and through our understanding of the Carnot cycle, we know that the Carnot cycle gives us the maximum efficiency. For any cycle operating between two temperature limits, Carnot engine, as it is a reversible engine or reversible cycle, it gives us the maximum efficiency. No practical cycle can give us efficiency more than the Carnot efficiency. But still, Carnot cycles are not making it practicable. It is difficult to make them practicable. And what are the reasons for that? Let us see. Though the Carnot cycle is simple thermodynamically and has a highest thermal efficiency for given values of T1 and T2, it is extremely difficult to operate it in practice because of the following reasons. It is difficult to compress the wet vapor isentropically, that is this process 3 to 4. It is difficult to achieve in practice because vapor is mixture of that is mixture that point 3. It is a mixture of water vapor and the steam, and it is difficult for any type of compressor physically to handle this type of mixture. If it is completely liquid, then a pump can operate. If it is completely a gas, then a compressor can operate it very easily. But if it is a mixture of these two things, then it is very difficult for the handling and also to maintain the isentropic compression. So it is difficult process. It is difficult to control the quality of the steam, condensate chemical of the condenser, so that steam state can be exactly obtained. We have to terminate the process of condensation exactly at point 3 so that we can reach to point 4 isentropically, and that termination is very difficult. The efficiency of the Carnot cycle is greatly affected by the temperature T1 at which the heat is transferred to the working fluid. Since the critical temperature for steam is only 374, yesterday you might recall that when we were talking about the steam tables, I told you that the critical value of temperature for the steam is 374. So 374 is the highest limit. Okay, and what is the lowest limit at heat rejection? Normal atmospheric temperature, means say 30 degrees Celsius. So only the temperature limit of 374 degrees Celsius to 30 degrees Celsius, this much limit is available, and that's why the Carnot cycle is, if you want to operate it within the wet region, and that's why avoiding the confusion of the processes 4 to 1 and 3 to 1, 2 to 3 sorry, then we need to operate it in the wet region only, and the maximum possible temperatures are limited, that is 374 and 30 degrees Celsius, because of the efficiency is getting limited. That's why this cycle is more difficult to operate in practice with superheated steam due to the necessity of supplying the superheated steam at constant temperature instead of constant pressure. And as constant temperature, maintenance is compulsory in the Carnot principle. That's why it is difficult to achieve this type of process in practice. In practical cycle, limits of pressure and volume are so far easily realized than the limits of temperature. So that at present, no practical engine operates on the Carnot cycle, although all modern cycles aspire to achieve it. Yeah. Every modern cycle, every power cycle is trying to achieve the efficiency of the Carnot cycle. That is the maximum possible efficiency. Now, what is modification done in the Rankine cycle? In the Rankine cycle, what is done? Two things important. One is the constant temperature processes are replaced by the constant pressure processes, means the heat addition process and the heat rejection process. Both are the constant pressure processes in the Rankine cycle, which are practically easily achievable, and that too we can range the process right from the subcooled region, subcooled water region to the superheated region without any difficulty. Okay, and second thing is that as we are achieving superheated steam, the reduction in the moisture content into the turbine, when the steam is entering into the turbine, that turbine moisture content reduces, and that greatly reduces the problem of erosion of the turbine blades, which is a very very important practical problem. So that is the modification. Second modification which was there in the Rankine cycle in comparison with the Carnot cycle is the process of condensation. The process of condensation was terminated in Carnot cycle simply to achieve the process 3 to 4 in an isentropic fashion, particularly in the wet region. But as this process of condensation, now it is a constant pressure process, we can allow it to get completed, we can allow that water to get completely the steam to completely converted into water, and then simply by using a feed pump with minimum possible energy, we can feed it back to the boiler. So here what we are achieving is a practicable cycle, although the efficiency of this cycle is greatly reduced because of these changes. The constant pressure processes are there to replace the constant temperature processes, and because of that the efficiency is getting reduced. And now instead of the temperatures, these fixed temperatures, we have to rely, while calculating the efficiency, we have to use the average temperature of the heat addition and heat rejection processes. Now if you represent the process of Carnot cycle on, say, let us start with TS plane. So this is the process 4 to 1 double dash, that is the process of heat addition. Now this 4 is the point at which the water is being fed into the boiler, okay, and at 1 dash, 1 or 1 double dash, the steam may come out. Means at 1 dash it is a wet steam, at 1 it is dry and saturated steam, and at 1 double dash it is superheated steam. So the process of expansion will begin from point 1 dash, 1 or 1 double dash. Preferably it should be 1 double dash. And you can see that if you are expanding it from 1 dash to 2 dash, or 1 to 2 and 1 dash to 1 double dash to 2 double dash, all these three processes are isentropic in nature, but the change is here. When we are reaching to point 2 double dash, the dryness fraction is less. At point 2 it is slightly higher, and at point 2 double dash it is the highest. Okay, and this steam which is coming out from the turbine, as it is very wet, when it is coming out at point 2 dash, it is going to cause erosion of the turbine blades. So to avoid the erosion of the turbine blades, it is normally advisable to go for the superheated steam, so that at the end of expansion we will get more drier steam, preferably if it is coming out at dry conditions or superheated condition, that is good, better. And then of course for that we need to reject more amount of heat into the condenser. Now here you can see that the heat which is rejected in the condenser, when you are shifting from process 2 dash say to 2 double dash, is H2 double dash minus H3 or H2 double dash minus H3. So naturally the second value is higher. It means that when we are trying to achieve the superheated conditions, we have to use higher capacity condensers. प्रत्येक गोष्टीला if there is advantages, then there is some limitation or disadvantages associated with that. At one end we are trying to achieve the superheated steam resulting into reduction in the turbine erosion. At the second point, we need to design the condenser with larger surface area so that it can be used for more rejection of the heat, and that will of course increase the requirement of water. So it's a judicious decision has to be taken. We cannot go for very high superheating, because superheating normally not results into increase in the thermal efficiency. Some extent thermal efficiency will get improved because of the superheated steam, but superheating is not advisable just for improvement in the thermal efficiency. Instead of that, we can go for some reheating or regeneration processes. Basically, what you need to draw, what you need to understand from this processes, first and very important point is from the Carnot cycle. As I told you, if you want to improve the efficiency of Carnot cycle, the heat addition temperature shall be highest and heat rejection temperature shall be lowest. But when you are shifting from Carnot cycle to Rankine cycle, we are not having the constant temperature. Temperature of 0.4 is different than temperature of 0.1 double dash or temperature 1 dash or temperature of 0.1. Similarly, the heat rejection temperatures here they are same because it is happening in the wet region only. So temperature at 0.2 double dash is equal to temperature of 0.3. But if this 0.2 double dash is in the superheated region, then this temperature of that point is going to be different than temperature of 0.3. Then what we need to do in such situation, you have to find out what is the average temperature of heat addition and what is the average temperature of heat rejection, and we have to compare these two values. So in line with the Carnot cycle, I can say that if you increase the average temperature of heat addition for a Rankine cycle, and if you reduce that average temperature of heat rejection, you will get better efficiency. Of course, it is not possible to achieve the efficiency of Carnot cycle through Rankine cycle devices, but still we can achieve higher efficiencies if you could increase the temperature of average temperature of heat addition and average temperature of heat rejection. So whatever efforts we are taking, it may be superheating, it may be reheating, it may be regeneration. All these efforts are concentrated on these two aspects only. Either to increase the average heat addition temperature, or to reduce the average heat rejection temperature. Normally the heat rejection temperature is not at all in the control, because it is the atmosphere to which we are supposed to reject the heat. We are not having another sink which is ready to accept all that amount of heat. Okay, so as the sink is fixed and the sink temperature is fixed, we have only one alternative in our control, that if you want to improve the efficiency of Rankine cycle, we have to rely on improvement in the average temperature of heat addition. मी परत एकदा सांगतो, if you want to increase the thermal efficiency of Rankine cycle, only one possible solution is increase the average temperature of heat addition. And that is what is done during reheating, that is what is done during the regeneration or even superheating to some extent. Okay. Now let us study the HS diagram, because we are going to use this for finding out the properties of the steam while solving the numerical problem. So here you can see that yesterday we have discussed about this particular HS diagram, that is Mollier diagram. But here it is completely shown, means the wet region is also, the subcooled region is also shown. So this is the subcooled water region, this is the wet region, this is the what you call saturated liquid line, this is the saturated vapor line, and this is the point where they are meeting. That point is called as the critical point. Okay, and now the processes are shown. 3 to 4 is a constant entropy process, so it is shown vertically. 4 to 1 is heat addition at constant pressure. You can see the pressure is constant, and either we can reach to 1 dash, 1 or 1 double dash, and subsequently 2 dash, 2 or 2 double dash. Here it is missing, it should be 2 double dash. Then process 2 double dash to 3 or 2 dash to 3 or 2 to 3 is again constant pressure process when the heat is getting rejected. Okay, and these are the things processes are explained over here. Reversible adiabatic expansion in the turbine, that is process 1 to 2. 2 to 3 is the constant pressure heat transfer to the condenser, into the condenser. 3 to 4 is reversible adiabatic pumping process, and 4 to 1 is a constant pressure transfer of heat into the boiler. So process number 4 to 1 is boiler, 1 to 2 is turbine, 2 to 3 is condenser, 3 to 4 is pump. So already we are having this. Now how to find out the efficiency of this cycle? So you have to use the steady flow energy equation for that. Already I think I have discussed about this in the last but one lecture, that how we apply the steady flow energy equation. So if you apply the steady flow energy equation, that is the first law of thermodynamics basically, to all these processes, because all these are flow processes, we are getting very simple equations like this. That is, if you want to find out the value of heat added into the boiler, you have to simply find out the difference in the enthalpy after the boiling process and enthalpy before the boiling process, means H1 minus H4. Now here it is, instead of H4, HF4 is written. Simply indicates that H at point 4 the liquid is there. It is not steam, it is a subcooled liquid at point 4. So that's why it is written, instead of H4 it is written HF4. Then for a turbine, work of turbine can be obtained just by simply knowing the enthalpy change into the turbine, that is H1 minus H2. Similarly, the heat rejected in the condenser can be calculated by knowing the enthalpy change H2 minus HF3. And for the feed pump, the work of the pump is HF4 minus HF3. And from that we can find out the efficiency of the Rankine cycle. What is the efficiency? Output upon input. What is the output? The turbine work minus the pump work. So net work, that is turbine work minus pump work divided by what is the input? The heat supplied into the boiler, that is Q1. So if we write down in terms of enthalpies, we will get this equation, H1 minus H2 minus HF4 minus HF3 divided by H1 minus HF4. Now in this the difficulty is that we can determine the value of HF3 easily from the steam table, but at point 4 is in the subcooled region. It is not in the wet region or not in the superheated region or not in the saturated line. It is unsaturated water. That is what is called as subcooled water. For determination of this properties of subcooled water, we have to either go for the subcooled water tables which are available in the literature, but instead of that we can have a simpler method for this. This method is obtained from using the general property relation for that adiabatic process. So this is the general relation. You might be recalling this TDS relation. TDS is equal to dH minus VdV. This is one of the TDS relationship. Here for this process the change in entropy is 0. So this equation will become dH is equal to VdV. That is, in terms of absolute values, it will be delta H is equal to V into delta V. Since the change in specific volume is negligible. Then we can write delta H is what? HF4 minus HF3, and that is equal to V3, that is the volume of steam at point 3 into P1 minus P2, that is delta V, where P1 is the boiler pressure and P2 is the condenser pressure. So these two values are known, and now we can arrange these things in this fashion, that is HF4 minus HF3 is equal to V3 into P1 minus P2. If you know the boiler pressure and if you know the condenser pressure in bar, you have to convert them into Pascal by using this multiplication factor 10 to the power 5. And then once you know the value of HF3, boiler pressure, the condenser pressure and the corresponding volume at point 3, we can easily calculate the value of HF4. But normally in very simple, if you want to make those calculations more simpler, then many times this pump work is ignored because it is very small in comparison with the turbine work, and that's why most of the calculations this HF4 minus HF3 term is ignored, and simply the Rankine efficiency is H1 minus H2 divided by H1 minus HF4, or HF4 is equal to HF3. Okay, when we are ignoring the pump work, directly we can take HF4 is equal to HF3. So simplified equation can be obtained, and this equation can be used for the efficiency of finding out efficiency of the Rankine cycle. Now just a brief comparison, just wanted to make comparison between Rankine cycle and the Carnot cycle. Following points are important. Between the same temperature limits, Rankine cycle provides higher specific work output than Carnot cycle. Specific work output means total work output, means how much work is obtained per unit mass of the steam. That is definitely more, because in Carnot cycle large amount of work is required for compressing that mixture of water vapor and steam. But here, as only water is there, the pump work is negligibly small, and that increases the net work obtained from this cycle. This simply means that net work obtained from the Rankine cycle is more as compared to the Carnot cycle. But of course, because of that, Rankine cycle requires smaller steam flow rates, resulting into smaller size of the plant for a given power output. However, Rankine cycles for higher rates of heat transfer into the boiler and condenser, which is very important. Since the Rankine cycle only part of heat is supplied isothermally at constant higher temperature, therefore its efficiency is lower than the Carnot cycle. The efficiency of the Rankine cycle will approach that of Carnot cycle if the superheat temperature rise is reduced. It's a problem. If you reduce the superheating temperature, then only the temperature or the efficiency of the Rankine cycle will approach the Carnot cycle. So superheating in that term is not desirable efficiency point of view. But already I told you that superheating is desirable for reducing the erosion of the turbine blades. Okay, superheating to some extent increases the efficiency, but it is more in terms of erosion, reduction in the energy, erosion of the turbine blades. It is essential. The advantage of using the pump to feed liquid to a boiler instead of compressing wet vapor is obvious that the work of compression is very large compared to the pump, and that is the comparison point. So, if you figure 10 point, next figure, the plots between efficiency and specific steam consumption against boiler pressure for Carnot and Rankine cycles are shown. Here you can see here the boiler pressure. You can see as the boiler pressure is increasing, efficiency of Rankine cycle is increasing, and around at 150 to 200 bar pressure we are achieving the highest efficiency of the Rankine cycle. And similarly for Carnot cycle also around the same range of pressure we are getting the maximum efficiency, but you can see the difference in the efficiencies. The peak efficiency of the Rankine cycle is of the order of 50%, whereas the peak efficiency of the Carnot cycle is of the order of 70%. And same is available in terms of the specific steam consumption. That specific steam consumption goes on reducing as the boiler pressure increases, and the specific steam consumption for Carnot cycle is higher than the Rankine cycle, simply because more steam is required for producing the same work, as more work or more power is lost in driving the compressor. Okay, so on one side Carnot cycle gives us better efficiency, but it needs more steam flow rates. Rankine cycle gives us lesser efficiency, but it also at the same time needs lesser flow rates, means lesser size, compact size of the power plant. So these are some comparison points of the Carnot cycle and the Rankine cycle. Now just few ways are there for basic conditions. This can be achieved efficiency improvement, effect of operating condition on the Rankine cycle efficiency. Rankine cycle efficiency can be improved by increasing the average temperature at which heat is supplied and decreasing the reducing the temperature at which heat is rejected. Already तुम्हाला सांगितलेलं आहे की if you increase the average temperature of heat addition, efficiency will improve. If you reduce the average temperature of heat addition, the efficiency will reduce. So I am just taking a pause, and I am expecting if you are having any question, you can ask me. Of course, through your screen. Good. So let us continue. Now I just wanted to declare that this much things were already learned by you. मला वाटतं सगळं तुम्ही शिकलेलं आहात. So how we can improve the efficiency by we can do it by increasing the boiler pressure. We can do it slightly by improving the efficiency by superheating and by reducing the condenser pressure. Of course, condenser pressure is difficult to reduce because reduction in the condenser pressure beyond the atmospheric condition results into a evacuated chamber, and it is difficult to maintain that chamber. But normally the high temperature or the high power producing steam power plants are having the condenser, they are running always under vacuum, and that's why the analysis is very interesting. Okay, we'll see this analysis of the condensation in the next unit. Okay, so I think this much is known to us. Now we can see that shall I give you example? This one example we will study so that you can recall the things. The following data refers to a steam power plant. What is the data? Inlet to the turbine, we got the pressure equal to 60 bar, the temperature is 380 degrees Celsius. Exit to the turbine, we got pressure is 0.1 bar, which is less than atmospheric pressure, 0.1 bar. What is the atmospheric pressure? 1.01325 bar. What is the current, what is the actual pressure? It is 0.1 bar, so it is under vacuum. Okay, and the quality of the steam, that is dryness fraction, is 0.9. Exit from the condenser is same pressure, slight reduction in the pressure. Instead of 10 kPa, there is 9 kPa pressure and 0.09 bar, that is, and it is coming as a saturated liquid. And exit from the pump and inlet to the boiler, once again the pressure has increased up to 70 bar. Okay, and exit from the boiler, okay, it is coming out at 65 bars. Means there is reduction is in the boiler, there is 5 bar reduction in the pressure. Okay, and when it is coming out from the boiler, it is 400 degrees Celsius temperature, and when it is entering into the turbine, it is 300. So what we have to do, we have to use all these temperature and pressure things for finding out the respective enthalpies. Another important thing which is given here is the steam flow rate, and that is 1000 kilograms per hour. Another value which is available here is velocity of the steam when it enters into the turbine. Okay, when it comes out from the turbine is 200 meter per second. Let us see where we can use this. What we need to calculate is the power output of the turbine, heat transfer per hour in the boiler and condenser separately, mass of cooling water circulated per hour in the condenser. Choose the inlet temperature of cooling water at 20 degrees Celsius and 30 degrees Celsius exists at the condenser. Means whatever cooling water you want to use for this condensation purposes, the inlet temperature of that is 20 degrees Celsius and the exit temperature is 30 degrees. Means the condenser water is increasing by 10 degrees Celsius. Simple. The diameter of the pipe connecting to the turbine with condenser. This is where we need this velocity, of course. The diameter of the pipe connecting the turbine with the condenser. The flow rate is 10,000 kg per hour, okay, and the velocity is 200 meter per second. And for that, we have to find out the diameter of the pipe connecting the turbine with the condenser. So let us see how it has been done in this problem. Let us first find out the power output from the turbine at first condition, that is 60 bar and 380 degrees Celsius. The enthalpy from the steam table is determined, and it is found to be by using some interpolation techniques. Directly you can do it from the property tables, of course, the steam tables, and it has got it equal to 3123.5 kilojoules per kilogram. So this is where you need to use the Mollier diagram or steam table. Then H2 at 0.1 bar here, that is after the exit to the turbine, the value of the HF2 is 191, HFG2, that is latent heat of vaporization from the steam table, it is 2392.8, and the dryness fraction is given to 0.2. So we can use this equation already familiar to you, HF plus X HFG, and we'll get the enthalpy of the steam leaving the turbine as 2345.3. So power output from the turbine is that change in enthalpy, that is H1 minus H2 into the mass flow of the steam, that is H1 is now known to us, that is 3123.5, and H2 is also known 2345.3. We take the subtraction multiplied by the steam flow rate. Now the steam flow rate is given in 10,000 kilograms per hour, so you have to convert it to kg per second. So it divided by 3600 to convert it into kg per second. So 10,000 divided by 3600. So this term is kg per second multiplied by kilojoules per kg. So kg per second multiplied by kilojoules per kg. What will happen? Kg will get cancelled and you will get kilojoule per second, that is in kilowatt. So answer is 2162 kilowatt. So this power plant is producing 2162 kilowatts of energy. Okay, correct, means almost 2.1 megawatt. Hence the power output from the turbine is 2162 kilowatt. Now heat transfer per hour in the boiler and the condenser. For that we need the value of properties when it is coming out from the condenser and it is coming out from the boiler, because at the entry to the condenser already we know this is the condition, that is at point 2, exit from the turbine and inlet to the condenser, this is the same condition, so the enthalpy will remain same, and exit from the condenser and inlet to the pump, it is saturated liquid at this point. Okay, so we need to find out the enthalpies of the respective points, and here it is done at 70 bar pressure, that is when it is entering into the boiler, the value of HF4 is 1267.4, and at 65 bar when it is entering into the boiler, when it is coming out from the boiler, 65 bar and 400 degrees Celsius, so enthalpy can be calculated once again by using the interpolation, and this interpolation gives us the result equal to 3167.6 by interpolation. Okay, and now we got the enthalpy of the liquid which is entering into the boiler and enthalpy of the water, steam when it is leaving the boiler. So we take the can say subtraction of these two parameters, that is H alpha or A, what is called here, HA minus HF4, you will get the heat rate into the boiler multiplied of course by the steam rate. So same calculations here not mentioned about the what you call it is found to be 1.9 into 10 to the power 7 kilojoules per hour. If you divide it by 3600, you will get in kilojoules per second or watt. Then at 0.09 bar, when it is coming out from the boiler, it is coming out from the condenser, the efficiency is the enthalpy is 183.3 kilojoules per kilogram, and heat transfer into the condenser is H2 minus HF3, and once again using this we got the heat transfer into the condenser is 2.16 into 10 to the power 7 kilojoules per hour. Okay, now mass of cooling water required. See, just wanted to recall that the mass, the temperature of the cooling water was changing from 30 to 20 to 30, and the heat which is given to this cooling water is equal to the heat rejected by the condenser. So heat loss by the steam into the condenser, that already we have calculated. Q1 matlab chunki it should be Q2, okay, and that is 2.16 into 10 to the power 7. So here it is, you can see this value is taken here. Mass of water to be calculated, Cp of water is 4.18, and the temperature change of water is 20 to 30. So using this, mass of water is calculated. You can see that 1.116 into 10 to the power 7 kilograms per hour huge amount of water is required for cooling into the condenser. This itself indicates that how much water is required for just producing 2 megawatts of energy. Okay, so you can imagine now how much water is needed for 100 megawatt, 200 megawatt or 500 megawatt power plants. Now diameter of the pipe, this is once again the continuity equation. Pi by 4 d square into c, that is the velocity, means area into velocity is equal to mass flow rate into the volume. So using this continuity equation, simply by using this equation we can find out the diameter, and the diameter of the pipe which is joining the condenser to the turbine has to be 483 millimeter, means almost half meter. Okay, this is a simple example which shows that how we can calculate the enthalpy and how we can use those enthalpies for finding out the performance of the Rankine cycle. So this is, of course, we already done it in second year, just recalling those things. So that now I'm skipping the modified Rankine cycle because I don't know whether it is covered in the second year syllabus or not, but modified Rankine cycle or this is only needed for steam engines, and nowadays we are not using the steam engines. Okay, instead of that we are using the turbines. So modified Rankine cycle is not important for current scenario, or important, but still there in the books we can ignore those concepts. Now in the next lecture I will be talking about the syllabus of our, that is, regenerative cycle. What is the meaning of regeneration? We'll see what is, how the regeneration process occurs, and we'll see how these things can be analyzed. You can see here, just I wanted to give you a hint so that you can prepare your minds according to that. You can see a boiler is there, then there is a superheater. The steam is entering into the turbine, and whatever things are happening, they are happening into the turbine only. And then it is followed by condenser, pump. So boiler, condenser and pump, they are intact, no change. We are not talking about regeneration. Only what is the change? There is something additional attached with the turbine. You can see that there are heaters. There are two heaters here. You can see HP heater and LP heater. Now we'll see why these heaters are needed and what is the effect of all these heaters and how it is resulting into improvement in the thermal efficiency by in the tomorrow lecture. Okay, we'll see the advantages, disadvantages and all those things. Then we'll see some of the problems in the next class, and after that, if the time permits, we'll be talking about the reheating cycles. Of course, it is possible to have two heaters or more than two heaters like that. Just wanted to show you, reheating cycle. So what is the meaning of reheating? That we'll do. Once again, it is a modification into turbine only. The results are shown in the PV and TS diagrams, and then we'll see how the things can be calculated by reheating. So this, it is expected that there may be some numerical problems based on the reheating and regeneration in your examination. So let's stop here. And we'll continue in the next lecture.